Good morning everyone. I am Rohit and today I am presenting my project EV ADAS dashboard using STM32 Blue Pill, PICSimLab and Python dashboard. The objective of this project is to develop a smart EV dashboard that monitors vehicle parameters, provides EV ADAS safety features. We use the STM32 Blue Pill for processing, PICSimLab for hardware simulation and Python dashboard for real-time visualization. In slide 2, we can see why smart EV dashboards matter. The problem: modern EVs generate vast time real-time sensor data, speed, battery, SOC, motor temperature, torque, and range. Without a centralized dashboard, engineers risk missing critical faults or collision warnings. The solution of this problem are real-time speed, SOC, and range display. Motor temperature monitoring, ADAS solution and blind spot detection, multi-level alarm system, live Python dashboard via UART, driving modes selection, eco, normal and sport mode. And also we can see our dashboard displays all vehicle information in one place, provides ADAS features like forward collision, blind spot detection, parking assistant, and overspeed warning to improve safety. System architecture and data flow. Sensor data from the accelerator, brake, battery, motor temperature and ultrasonic sensors is sent to the STM32. The controller processes the data, calculates EV parameters, performs ADAS functions and sends the information through UART at baud rate 115200 baud to the Python dashboard for real-time monitoring. 9 phases of development. The complete project was divided into 9 phases. Involved setting up the software tools and simulation environment. In second phase, focus the GPIO pins, timers, ADC channels, PWM outputs, and UART communication. The third phase involved reading sensor values using ADC. The fourth phase implemented the EV dynamics model for calculating vehicle speed, torque, battery, SOC, and driving range. The fifth phase added ADAS features, ADAS safety functions. In sixth phase, implemented the fault detection and alarm generation. In seventh phase, established UART telemetry communication. In eighth phase, developed a UART command shell for testing and debugging. Finally, the ninth phase created a Python dashboard to visualize all vehicle information in real time. Phases 1 and 2: environmental setup and GPIO. For firmware development, we used STM32 which develops programming, debugging, and peripheral configuration to simulate the embedded hardware without physical components. We use PICSimLab. The Python dashboard was developed in using PySerial library for serial communication, NumPy for calculations, and Matplot library for graphical visualization. During GPIO configuration, we initialized ADC channels for analog sensors, timers for periodic operations, PWM for buzzer control, GPIO pins for LEDs, and UART 1 for serial communication. These configurations form the foundation of the development of embedded system. In slide 6, we can see phases 3 and 4, ADC sensors and EV dynamics. In this phase, analog sensors were connected to STM32 through ADC channels. Using these sensor values, the STM32 calculates important vehicle parameters such as vehicle speed, torque, battery, SOC, and estimated driving range. The system supports three driving modes: eco mode, normal mode, and sport mode. Regenerative braking system is also implemented so that energy generated during braking helps recharge the battery, increasing vehicle efficiency. In slide 7, we can see ADAS engine and fault alarms. Ultrasonic sensors detect nearby obstacles. The system provides forward collision warning, blind spot detection, parking assistant, and time to collision war calculations. It also detects faults like low battery, motor overheating, sensor failure, and collision risk, and generates advisory, warning, and critical alarms. Phases 7 and 8 your telemetry and shell. The STM32 sends vehicle and ADAS data to the Python dashboard every 100 milliseconds using UART. The UART shell supports commands like speed, SOC, temp, mode, fault, reset, and status for testing and debugging. Slide 9 Python dashboard. The dashboard displays vehicle speed, battery SOC and range, motor temperature, torque, ADAS bird's eye view, speed history graph, and alarm level and fault status. This allows real-time monitoring of the vehicle. Conclusion: this project successfully integrates EV dynamics, ADAS, UART communication, and Python dashboard into one smart monitoring system. It improves vehicle monitoring, safety, and reliability, and can extend it in the future with GPS, IoT, cloud connectivity, and ADAS assistance. It demonstrates how embedded systems and software visualization can work together to build an intelligent and efficient EV monitoring solution. Overall, this project provides a cost-effective, scalable, and real-time platform for developing next-generation smart EV applications. I would like to explain the software demo of our EV ADAS dashboard project. First, I am opening STM32 Cube IDE. This software used to write debug the program for the STM32 Blue Pill microcontroller. On the left side, we can see our project named EV ADAS. This project contains all the files needed. I expand the project folder. Under we can see the core folder. I can open the source folder and then open the main.c file. The main file where our program starts. At the top of this file, we can see the header files like main.h, stdio.h, string.h, common.h, and ev underscore control.h, ads.h, fault.h. This file contains different parts of our project. For example, an ultrasonic is used for distance sensing and ADAS is used for safety features, fault checks for errors, and UART shell handles the serial communication. Now we can see the EV ADAS and fault objects. This store important information like vehicle speed, battery level, motor temperature, obstacle distance, collision warning, and fault status. Below this, we can see the timer interrupt callback function. Timer 1 runs every 10 milliseconds and update the EV data. Timer 3 runs every 100 milliseconds to update the sensor values and ADAS features. This helps the system work in real time. In main function here, STM32 initialize all the required peripherals like GPIO, ADC, UART, and timers. After that, the timers are started, UART interrupt is enabled, and the all modules such as EV control, ultrasonic sensor, ADAS fault detection, and UART shell are initialized. After initialization, the program enters the while loop, which runs continuously. Inside this loop, the controller reads the accelerator, brake, and motor temperature values. Using these values, it calculates the vehicle speed, motor torque, battery percentage, and driving range. Here we can see while loop, fault check, ADAS update. Every 100 milliseconds, the ultrasonic sensors measures the distance of nearby obstacles. Then the ADAS module performs forward collision warning, blind spot detection, parking assistant, and time to collision calculations. The fault detection modules also checks for the problems like high motor temperature, low battery, sensor failure, and communication failure. If any of these problem is detected, it generates an warnings like advisory, warning, or critical or normal warning. The print status function sends all the EV and ADAS data to the Python dashboard through UART communication. The dashboard displays speed, battery level, temperature, torque, range, obstacle distance, alarm level, and fast status. The UART receive callback function receives commands from the serial terminal. We can see the commands like speed, SOC temp, mode, fault, reset, and status to test the different conditions. This is the code of our project. Finally, I open the ev-ioc file. Here we can see the pinout configuration where GPIO pins and peripherals are configured. In pinout configuration, we can see pinpoint view, pinpoint view, GPIO pins and peripherals. Next, we open the clock configuration where the system clock settings are configured. Finally, I click the build project. After build is completed, the console shows 0 errors, 0 warnings. This means our program has compiled successfully and, and it is ready to run. This completes the STM32 Cube IDE demonstration. Next, I will demonstrate the PICSimLab simulation and the live Python dashboard. Here we can see the STM32 Blue Pill board. In that, go to the modules and select spare parts. In spare parts, we can see 3 ultrasonic sensors and 4 potentiometers and 4 LEDs and buzzer and IO virtual term. As we change the distances of ultrasonic sensors, we can see the output in the IO virtual term. Here is the distances of, here is the output of the 3 ultrasonic sensors and potentiometers. When we decrease the first ultrasonic sensor, and here red LED is glowing. This shows collision alert. As we decrease the left ultrasonic sensor, here we can see the blue LED. This shows left blind spot detection. As we decrease the third ultrasonic sensor, distance shows right blind spot detection. These all values can see in virtual term. Here alarm 0 means normal, alarm 1 means advisory, alarm see the alarm 3 as the warning is critical. We use VSPA to create a pair of virtual compounds. Now select the VSPA. Continue with limitations. Go to the device. Now go to the virtual pair. Then go to next. Select compound 1 and port 2. Select finish. Hence our VSPA port pairs are ready. Now go to the PICSimLab. Then go to file. Then configure. Select serial port as COM1 and save. Now go to command prompt. Now go to command prompt. Run as administrator. Yes. Here is the file name of our Python dashboard file name, and select port 2 and press enter. We can see the dashboard Python dashboard of our project, where we can see the normal mode, torque, accelerator, brake, motor temperature, alarm, fault, signal, and speedometer, and graph, and bird's eye view, and battery percentage. As we decrease the ultrasonic sensor distance, we can see the blind spot detection on left side. As we decrease the right ultrasonic sensor distance, we can see the blind spot detection at right. As we decrease the front ultrasonic sensor distance, it shows the alarm critical and the red LED blinks. We can see, and we can see the in bird's eye view. As we increase the acceleration pedal and SOC, we can see speed is increasing and battery is decreasing. This concludes our presentation on the UART dashboard project. Thank you for your valuable time and attention.